In this video, I'll show you 5 counting problems and how to solve them. The first problem: in how many ways can these 10 colors be lined up? Each lineup is called a permutation. For the color in the first position, I have 10 choices. For the second, 9 choices. And for the third, I've got 8 choices, etc. And for the last one, I have just 1 choice left. So the number of permutations of the 10 elements is a factorial of 10, more than 3 million. The second problem: in how many ways can I choose a set of 3 colors from this set of 10 colors? Well, each of these sets is called a combination. When I pick the first color, I have 10 options. For the second color, I've got 9 options. And for the third color, I've got 8 options. However, this same combination of 3 colors could have been picked in 6 ways. For example, blue first and then orange. Or like this, or like this, or like this. The same 3 can be picked in 3 factorial permutations. So in the 10 times 9 times 8 combinations, each combination is counted 3 factorial times. The number of different combinations is 720 divided by 6, which gives 120 combinations. Let's write this number into a more general form. Multiply the ratio by 7 factorial over 7 factorial. The number of combinations of 3 out of a set of 10 is 10 factorial over 3 factorial times 7 factorial. This ratio is called 10 choose 3, which is a so-called binomial coefficient. In general, the number of combinations of k elements out of a set of n different elements is n choose k and can be calculated by dividing n factorial by k factorial and n minus k factorial. Most often, ratios of integers have non-integer values. However, a binomial coefficient is integer. Maybe you want to prove that yourself. Something else: if we reverse the order in the denominator and write k as n minus k, we see that n choose k is equal to n choose n minus k. So, for example, 10 choose 7 is equal to 10 choose 3. So we can also make 120 combinations of 7 colors from the same set of 10. Is that surprising? No, for each combination of 3, there's exactly 1 combination of 7 left. Another example. What is 10 choose 0? In how many ways can I choose no color out of a set of 10? Well, 10 choose 0 is equal to 10 choose 10, which is 1, as there's only 1 way to choose the whole set. So there's also 1 way to choose no color from the set. In the calculation, we use that by definition: 0 factorial equals 1. The third counting problem. Say I want to make striped hats. I'll use the orange for the rim and the white and the blue stripes for the crown. If the crown has 10 stripes, how many patterns can I make? Well, for each stripe, there's a choice between 2 colors. So in total, there are 2 to the 10th patterns. In the same way, you can make 1024 different numbers with 10 binary bits. Now, more difficult patterns. Say I want exactly 4 blue stripes and 6 white stripes. How many patterns can I make now? If I now count the same way, choose a color for the first stripe, for the second stripe, for the third stripe, for the 5th stripe, there may not be any blue left. So the number of choices depends on the earlier choices, and this is not an easy way to count. Instead of choosing a color for each stripe, I'll do the reverse. I'll choose a position for each of the 4 blue stripes. For the first blue stripe, there are 10 positions. For the second one, there are 9 positions. etc. for the fourth one. And the other positions are filled by the white stripes. Of course, the order in which the 4 positions for the blue stripes is chosen is irrelevant. There are 4 factorial permutations for the order. So the number of different patterns is 5040 divided by 4 factorial. This gives 10 choose 4 patterns. And now the last counting problem. Say I want to make 3 different sweaters. A simple sweater, a cardigan and a hoodie. For each I need 10 skeins. This is a skein. I have 10 blue skeins and 20 white ones. How many ways can I distribute the blue skeins over the 3 sweaters? You may try this yourself, but for this problem I cannot count elements per position or positions per element. Instead, I'll use dividers. I'll put the 10 blue skeins in a row and I can separate them like this. Now, for example, for sweater 1, I have 2 blue skeins. For sweaters 2 and 3, I've got 4 blue skeins each. If I put the divider here, the first sweater has no blue and the second sweater has 6 blue skeins. I can even put both of them here and then I've got 2 white sweaters and the hoodie will be all blue. So now I only have to count the ways to line up 10 blue skeins and 2 dividers. The trick is to see the 2 dividers as elements that need 2 extra positions. So in how many ways can I distribute 2 dividers over 12 positions? For the first divider, I have 12 possible positions. For the second, I have 11 possible positions. And the other positions, of course, are filled by the blue skeins. The 2 divided positions, of course, can be permutated. So the number of ways to distribute 10 blue skeins over 3 sweaters is 12 choose 2, which gives 66 ways. Again, that's a lot of options for sweater design. I have shown you 5 cotton color counting problems. The number of permutations was 10 factorial. The number of binary patterns was 2 to the 10th. And for the 3 other problems, the number of combinations was a binomial coefficient.